as far as scan design rules are concerned, so there are several design styles, and for them, for some of them it creates difficulty while we are putting them putting the scan on top of that, and they are to be corrected or the design has to be modified. Like the tri-state buses. So, many of our designs they have tri-state buses. So, scan design rule tells that this tri-state buses be avoided during shift operation. So, because during shift operation, if some bus is tri-stated, then the pattern will not shift through that bus. So, we have to fix this bus contention during shift. So, we have to ensure that there is no bus contention occurring during the shift operation. Similarly, bidirectional input output ports. So, we have to force the input or output mode during shift. Somehow, we have to ensure that they become unidirectional. So, that way there are many issues that will be coming, which needs to be corrected in the scan design process. And as I have already said that these CAD tools are available which will do these things. So, once you have submitted a design to the tool, so for this scan conversion, so it will do that, it will rectify all those problems, and it will be coming up with a design which is correct. First one, the tri-state bus. So, here what has happened is that you see we have got a number of flip flops, okay, number of scan flip flop is there, and then they are so in this there is a bus contention like this. These are these D1, D2, D3 etc. So, these are actually some tri-state buffers, and from some logic these tri-state buffers, so they are getting the values. Okay. So, maybe in the normal functional mode of operation, so something the designer has done, so that these tri-state buffers will not be driven at the same time. But for the testing mode of operation, so we cannot rely on what has been done at the design level. So, what is done is that for the testing mode, so we need to modify it. So, how do we modify? So, we modify it like this, that in the scan enable mode, so this for the scan when this AC line is scan enable line is high, so it is going there. At the same time, this scan enable line, it is also coming to this, they are connected to an OR here and via complemented version here. So, EN1 is forced to 1 to enable the D1 bus driver, while EN2 and EN3 are set to 0 to disable D2 and D3. So, these two are disabled and this one is enabled. So, it ensures that during the shifting operation only this EN1 line will be high. So, only this value will be available on the bus. A bus without a pull up, pull down or bus keeper may result in fault coverage loss, because so that is why sometimes in the test mode, while going into the test mode, so we keep this bus keeper logic. So, it will be doing this, it will be keeping the voltage level is there. So, this type of fix may be added. So, what we are doing, out of so many enable lines that are there for this bus, so we are ensuring that only one of them will be enabled. So, rest are all disabled. So, this is done by means of doing this OR AND operation of this OR AND operation along with this enable lines. Then there are bidirectional IO ports, like say this is a structure where we have got this from an input output pin, bidirectional pin, there are buffers. So, this buffer is going putting the value to the buffered input. Similarly, the buffered output will go through this buffer and it will come to the output. So, this is a very standard design when we have got bidirectional IO. So, now the conflict may occur at a bidirectional IO port during shift operation. So, if we are trying to shift, then the value that we are maybe we are just willing to put it onto the next flip flop, but that way it may come back again as the input. The output value of the scan cell can vary during the shift operation. The output tri-state buffer may become active. So, what is happening is that so this is a scan flip flop. So, there may be a chain of scan flip flops. So, and this Q output may be actually driving this buffer. For the final test pattern, it may so happen that this Q output will not enable this, but in between it may so happen that some pattern that is shifting, while shifting, so this buffer becomes active. Okay. So, what we mean is this one, that I have got a number of scan cells. Okay. So, we are trying to set this scan chain to some value, maybe 1 0 1 0 1, say this value, but when it is shifting, so each of these cells they are seeing the values of ones and zeros. Maybe this bit is actually controlling that one enable line of a tri-state buffer, one enable line of a tri-state buffer. Now, ideally this should be enabled, but or maybe this is 0 and say this is 1. So, ideally this should be disabled for the final operation, but while I am shifting the pattern through this chain, so sometimes it is getting the value 1, as a result this buffer is getting enabled. So, that may create problem with the content of the circuit. So, output value of the scan cell can vary during the shift operation. The output tri-state buffer may become active, resulting in a conflict if this buffered output and the IO port driven by the tester have opposite logic values. So, tester has given some value here for shifting into the system, and this BO line is something else computed by the combinational logic. So, if these two values differ, then there is a conflict at this point. So, that has to be avoided. So, how to do this thing? So, for doing this, so this buffer has to be disabled. So, how do we do this? When the AC line is 1, here I am getting is 0. So, that this whatever be this Q value, so this AND gate output is 0, as a result this buffer is disabled. So, from this buffered output, so it cannot conflict with this IO bit value. So, that way it cannot get affected. So, whatever value the tester puts on this IO line, so that will come through this BI line. So, during the capture operation, the applied test vector will determine whether a bidirectional IO is used as input and output, and then it will and controls the tester appropriately. So, that is the scan shifting time for the or scan enable time, but when it is actually the capture cycle, then of course this is 0. So, this is 1. So, it depends on this Q setting, and that is actually decided by the combinational logic coming through this DI input. This Q is set. So, if this Q is 1, then this buffer may be enabled. As a result, whatever is the BO value will come to the IO, and that in turn will go to the tester. That will go to the for as the response pattern. So, that can happen. Another very important design style that we have is the clock gating circuit. So, clock gating is done so that we want some portion of the circuit to become inactive for power consumption point of view. So, this is a good approach for reducing power consumption, because if we want that say in a typical sequential circuit design, as I have said that there is a combinational logic and there are flip flops. Okay. So, there are flip flops which are feeding this combinational logic. Now, if we want that if we find that for some time this system should not work, it should not work means its output is not that much that necessary. So, what we can do, the clock signal that we have, so we can disable this clock signal, so that these flip flops will not change their values, and if they do not change the value, this combinational logic will also not get any change in this pseudo primary input, and possibly it will not change the pseudo primary output as well. You can also have some sort of latch here to ensure that the primary inputs are also not changing, so that this combinational logic becomes totally idle. Now, this is known as clock gating. So, to do this clock gating, what we have to do is put some sort of say AND gate. So, here I have got the actual clock signal, okay, and I have got the some enable line here. So, this enable line, when enable is equal to 1, then the clock will go. If enable is equal to 0, then the clock will not go. So, what happens is that in this case, so I have got this outputs driving this clock gating logic. Clock gating logic generates this enable signal, and this enable signal is latched here, and then this is ANDed with the clock, and this finally generates the clock enable. So, this clock enable line is generated, and that is the gated clock given to the final D flip flop, where we should have connected the clock line. So, this is a popular approach for reducing power consumption as it prevents the clock ports of some flip flops from being directly controlled by the primary input. However, it has got difficulty because during shift operation, so there may be problem. Okay. So, there what happens is that the clock gating function should be disabled at least during the shift operation. So, how do we do this thing? So, this test mode or this shift enable mode. So, at that time, so or this enable signal. So, in these cases, so this OR gate output is connected to this D input. So, that this latch value will be coming here, and then this OR gate is used to force this this clock enable value to 1. So, this in test mode or in shift enable mode. So, this OR gate output will be 1. As a result, this CEN output of this flip flop will definitely be 1. So, this AND gate will and so that clock enable line is high. So, this flip flop will always get the clock if this TM or AC is high. So, in the test mode, whatever this clock gating logic computes, so that is getting overwritten by this TM or AC signals. So, that way the gated clock problem can be resolved. Sometimes we have got derived clock. So, derived clock means from one clock signal we derive some other clock signal internally. So, like this. So, I have got one clock CK and I have put an inverter and connected to D flip flop. So, that this clock will be divided by 2, I think. So, so that it is it will be generating the D is continually whenever D is 1. So, this will become 1, then this is 0. So, this will become 0, but that will happen at the half the clock rate that we have here. So, this is a clock divider type of circuit, and then this derived clock is given to the 2 D flip flops. Okay. So, this is the derived clock circuit. Again, the problem is that now this shifting pattern through this all these flip flops, when they converted into scan flip flops, the shifting pattern becomes a different for different portions. Okay. So, we have to bypass this. So, what is done? So, we put a multiplexer here. So, this for the normal operation of the circuit, this test mode is off. As a result, whatever is the derived clock, so that will go to the flip flop. But in case of test mode, if test mode is on, then this clock value that is coming, so that will go directly into this D flip flop. So, this derived clock does not have any meaning here. So, this is required, otherwise these flip flops we cannot convert to scan flip flops. So, because they will be driven by a different clock in that case. Okay. So, this derived clock is another obstacle for this scan shifting, and that is resolved by introducing this type of modification. Then there may be combinational feedback loop. So, here what has happened is that I have got this combinational logic, its output is again feeding the input. So, that way there may be some combinational feedback loop. So, depending on whether the number of inversions on a combinational feedback loop is even or odd, it can introduce either sequential behavior or oscillation into the design. So, you can count the number of inverters. So, naturally, if I have got a situation like this, there is a single inverter, then if this inverter is initially 0, then it will immediately after one clock cycle, after some time, depending upon the delay of the inverter, it will become 1, again after the delay it will become 0, after some time it will become 1. So, that way it becomes an oscillatory behavior, and similarly if it is even, then it will show that this will be this will have some sequential behavior. So, that way we have got different undesirable behavior of this combinational logic. So, the best way to resolve this combinational feedback loop is to rewrite the code, and we have got a better design that does not have these combinational feedback loops, because the loop the value stored in the loop cannot be controlled or determined during test. So, this can lead to an increase in the test generation complexity or fault coverage loss. So, how to solve this problem? So, for solving this problem, what we can do? we can in the test mode this TM signal. So, this signal permanent is so this signal when TM is equal to it will disable the loop throughout the entire shift operation, shift and capture operation by inserting a scan point to break the loop. So, this point is actually observable point. So, this is going from when this clock signal, when this TM line is high, then this point becomes visible. Okay. And this otherwise this D point that we have, so that is actually coming to this data input line. So, we can see the value of this Q point through this. Asynchronous set reset signals, like if we have asynchronous set reset signals, then that creates difficulty, because this flip flops they may become reset arbitrarily. So, in the original circuit what has happened is that whenever this Q value becomes 0, so it resets this particular latch. So, this RL signal is generated. So, this latch gets disabled, this latch gets reset. So, this has to be prevented, because they are not controlled directly from the primary inputs. So, we have to prevent this type of resetting, because when the patterns are shifting through this through these latches, it may so happen that some intermediary point this value becomes equal to 0. As a result, this latch gets reset. So, that has to be avoided. And for doing this thing, again the way we have to do it is that this under the test mode, this TM line, this RL is put through an OR gate. So, this Q output and this TM, so they will be ORed here, and then it will go to this thing. So, if the TM is high, then this RL will always be 1. As a result, this latch will never be reset as long as the test mode is on. So, that way it can avoid resetting of this latch 2. Now, in the scan design flow, how this has to be done? Like we have seen that there are several scan circuits, several ways of converting flip flops to scan flip flops. We have seen that there are some set of design rules for that. Now, how they are taken care of in the whole design process? So, this original design, so it goes first it goes through a scan design rule checking and repair. So, this actually corrects all those problems, like say clock gating or this asynchronous reset. So, all those are taken care of, and the design is modified by this rule checking and repair part. So, that gives rise to this testable design. Once I have got this testable design, it goes into a phase which is known as scan synthesis. In the scan synthesis, there are several parts like scan configuration, replacement, reordering and stitching. So, at the reordering stage, we need this layout information, and then this also we need this constraint and control information. So, they are added into this one, into this scan synthesis process. That gives us the scan design, and after the scan design has been done, the scan is extracted and the test generation task is also started. So, tests are generated, scan chains are extracted, and the scan verification takes place, and this process continues again, so that if there is some flaw, then some problem is occurring, then again this scan synthesis part is repeated. So, we will see, we will look into this design flow. So, first part of this design flow is the scan design rule checking and repair. So, this is for identifying and repairing all scan design rule violations to convert the original design into a testable design. So, whatever design rules we have seen, the scan design rules we have seen, so they are checked, and if there is a violation, then they are corrected for making the design testable. And it is performed after scan synthesis to confirm that no new violations have occurred. So, after the modification has been done, so it should be the case that no new violation has occurred. So, again the rule checking has to be done. Then the scan synthesis, so it will convert the testable design into a scan design without affecting functionality of the original design. So, so it will be converted into scan design. So the flip flops will be converted to scan flip flops, the scan stitching and all that. So these are the various stages in it: scan configuration, replacement, reordering and stitching. Then we have got scan extraction. So it is the process used for extracting all scan cell instances from all scan chains specified in the scan design. So this will find out all the scan cells that have, all the flip flops that have been converted into scan cells, all the latches that have been converted into scan cells, and in which chain they are existing. Then there comes the scan verification. So this is a timing file in standard delay format, which resembles the timing behavior of manufactured device, is used to verify the scan shift operation and scan capture operation, whether those two operation delays are coming in proper timing or not. So this standard delay format file, so they will have this timing information. So what are the costs of this scan design? Definitely area overhead is one thing, like we have converted many of them into scan cells and all that. So that is there. Then there is IO pin cost, input IO pin cost. So this is basically the extra pins that are needed, like the scan in, scan out lines, then the clock, the SCK, scan enable, test mode, all these extra pins that we are talking about. So they are to be, we have to pay for that. So their pin cost is there, plus this clock distribution, this scan clock distribution is another issue. So that has to be taken care of. Then the performance degradation cost. So performance gets degraded because of the reason that some extra circuitry has been added. So that may come into the critical path of the design. So delay will increase. So and design effort cost. So that is the extra amount of man hours and the effort that needs to be put, so that this design testing, this scan insertion is done properly and testing can be carried out. So that is another issue. So what sort of scan design rule checking and repair can be done? Like you see that it may so happen that in my circuit there are several clock domains, like this CD1, CD2, CD3, CD4, CD5. So they are different clock domains. So what we mean is that all modules in this particular, in a particular region, they are driven by the same clock. Now it may so happen that from clock domain 1 to clock domain 2 there is a signal which is being passed. So they are called crossing clock domain data path, like this CCD1. So there is a path from CD1 to CD2 in the circuit. So that is actually crossing the clock domain. Similarly here CD1 to CD3. So there is a crossing clock domain, but from CD2 to CD3 there is no crossing. Okay. Now if there is no crossing, so what we can do is that we are trying to assign some clock values to these individual clock domains. So CD1 CD1 and CD2, they cannot be assigned the same clock because they are from two different clock domains and they are coming at there is some edge which is there is some data that will be coming from one clock domain to another clock domain. So we cannot group these two clocks together. So I have to give separate clocks for CD1 and CD2. So that is done, but between CD2 and CD3, so there is no such data transfer. So we can put them onto the same clock. So basically when the circuit is designed, at that time we may find that okay, they are different clock domains, but having so many different clocks in the system may be problematic. So the routing of all those clocks are difficult. So we may like to group some of these clock domains into a single clock, like CD2 and CD3, since they are giving data in the they are not interacting with each other, so they can be given the same clock. Similarly, CD4, 5, 6 and 7, they can be given a separate single clock. So ultimately this 7 clock domains that we have, so they can be clubbed into, or they can be merged into 3 such clock groups, CK1, CK2 and CK3. So this design rule, it may check this thing, that it may find that okay, if there is any violation or not. Then comes scan synthesis. The first part of this scan synthesis is scan configuration. So this will be the first input that we have is the number of scan chains used. So if I have got a single chain, then what will happen is that all the flip flops that I have, so they will be on that chain. So controlling individual flip flops in that chain becomes difficult. So that way it is a bit cumbersome. So the time to load the scan chain will be high. So that has to be taken care of. So it may be that if I am allowed to provide multiple scan-in lines, multiple scan-out lines, etc., then I can possibly go for multiple scan chains, where the individual scan chains will be smaller in length. As a result, the loading and unloading will be faster. So number of scan chains that are used, so that is one important issue. Second thing is that the type of scan cells used to implement these chains. So we have seen that there are several types of scan cells, like the masked D, then this two clock, then we have got LSSD. So like that we have got several types of scan cells. So which scan cells we are going to use for implementing these scan chains. Then which storage elements to exclude from the process. So as we have said, there is a partial scan design. So which one are to be excluded, which one are to be considered, etc. That is one thing. And how the scan cells are arranged. So what is the order in which these scan cells will be put. Then the scan replacement, it will replace all storage elements in the testable design with their functionally equivalent scan cells. So once we have decided to modify some of the storage elements to scan cells, so the scan replacement process will modify all those storage elements to the scan versions. Then we do a scan reordering. So reordering the scan chains based on the physical cell locations. So if because between two successive scan cells I should have a connection. So if the two cells are located far away, then the chain that the wire that will run will be long, and if there are, so I need to find a proper path for all these scan cells to be put onto a chain, so that the length of these interconnects is the minimum. So for that purpose I may need to reorder the cell numbers. Okay, so reorder the cells that have been identified, so that I can minimize the amount of interconnect wires. And finally scan stitching. So we have to stitch all the scan cells together to form scan chains. So the output of one scan cell should go to the input of another scan cell, like that. So those connections are to be established. So that is actually the scan stitching. So we'll continue in the next class.